These are the notes for Unit 3, Day 4. So take a second and pause the video and try this multiple choice question. If you are resuming the video, I'm assuming you've tried the question. We're going to go over the solution now. It says, which of the following requires the use of implicit differentiation to find the derivative, dy dx? So we are looking for something that requires implicit differentiation. So we're looking for something where solving for y is extremely difficult. So option A, solving for y requires taking the x terms to the right. That's okay. In option B, all the x terms are already on the right, so it's already solved for y. Option C looks like it's solved for y, but we have a y term here. And to get that out of the natural log would really require some pretty fancy exponentiation. That would be extremely difficult. And D is already solved for y. So A, we can use the power rule. B, we can use a combination of the power rule, the natural log, it looks like maybe even a chain rule here. This is where the implicit needs to be. Can't solve for y, we've got y in 2 locations. And this will, we'd use a quotient rule. So the answer here is C. Okay, so the notes start on page 12 of your note packet. And we're still working with this essential question, when do we use implicit differentiation? And we're going to look at a more complicated example now. So it says find the derivative by implicit differentiation. So 7 cosine 2x sine 3y equals 5. So again, solving for y here would give us this complicated inverse sine sort of function, or not function, excuse me, expression. And that would be nearly impossible to differentiate. This is what the expression looks like. So obviously not a function, right? The vertical line test doesn't pass it. Just looks like a bunch of little bubbles. Guess we could call this the bubble wrap expression. And so it's really not so important that you know what it looks like, but that you can do the implicit differentiation. I just like to provide a picture. Most often the graphs aren't provided, but it's kind of neat to see what these look like. As long as you have something that can graph implicitly. And not your calculator can't, but GeoGebra can, so it's kind of cool. Okay, so we're going to solve this implicitly and differentiate this. And excuse me, and so we have a product here. We have a cosine times a sine. So I see a product rule, and then I also see a chain rule because I see brackets, right? I've got a 2x, I've got a linear expression inside a cosine, and I've got a 3y that is inside a sine. So this is linear with respect to y, but we're going to need the chain rule to get it back in with respect to x. So let's just kind of go over that. We got a product rule, we've got a chain rule. And so, so it looks, I'm going to divide it up like this because the 7 is just a coefficient. So I'm going to, we actually could have divided out the 7 too. So I'm going to split it up like this. This is 7 cosine 2x, I'll call my u, sine 3y, I'll call my v. Okay, and so I'm going to go ahead and start with the differentiation. So my u prime, excuse me, my u prime would be differentiating this. I'm going to need a chain rule. So that's going to be outside derivative is going to be negative sine 2x, negative 7 sine 2x times the inside derivative, which is 2. So there's my u prime, right? Derivative of the outside times derivative of the inside with that chain rule. And then I have to multiply times v, so times sine 3y. And then I'm going to do my uv prime. So plus my u is the 7 cosine 2x. My v prime is differentiating sine 3y. So it's a chain rule. And it's also where you're going to see you have the implicit expression. So this is going to be times, now v prime is cosine 3y times 3y prime, right? That's the derivative of 3y because it's a y variable. We need that chain rule, that y prime. And that's what we're solving for. So we should have a y prime. And then derivative of 5 is 0. And so if we're looking at this, let's go back to the expression. We see y in one location, so we have y prime in one location. There's no collecting y primes. We only have the single one. So I'm going to take this and kind of simplify it, right? -7 times 2 is -14. So I've got -14 sine 2x sine 3y plus, I'm going to simplify this, 21 cosine 2x cosine 3y y prime equals 0. Okay, so I've got two terms. I'm going to move this term, this -14 sine 2x sine 3y, I'm going to move it over to the right-hand side by adding it. And it's going to cross out on the left. I'm going to be left with the 21 cosine 2x cosine 3y y prime. And on the right, I'm going to have the 14 sine 2x sine 3y. And this product now on the left, I can just divide out. And this cancels on the left, and I'm left with my y prime. So I'm going to change screens here. Now this is the same as what I had right here. Okay, so you should already have that written in your notes. Okay, I'm going to cancel out the stuff on the left. I'm going to be left with y prime. And now look at this. Okay, there's a lot of ways we can simplify this, and we need to be comfortable with that, because if this were a multiple choice question, we'd have to find the correct form of the answer. So this is what we have. So this is how we're going to look at this. We have the sine of 2x over cosine of 2x. We can rename that as tan 2x. We have sine 3y over cosine 3y. We can rename that as tan 3y. So we have 2/3, that's 14 over 21 reduced, tangent 2x, tangent 3y. And there's our derivative. And then if we can find a point on the function, which I'm not sure I can accurately find a point on the function, then we can find the slope of the tangent line or the derivative at that location. Okay, we'll go over the summary when we get back into class. And I think after that and the takeaways, I think this is, I think we're going to go into topic questions after those two things in class.